I have no special talents. I am only passionately curious. By Albert Einstein. I am Jason Mann. I am someone with passion. I am not a genius or smarter than the average person. I just have an insatiable curiosity of nature. I have always thought of myself as an average person with an extraordinary love for science. I want to share that curiosity, joy of learning, and about the physical world we all share. My goal is to give only the amount of information that is desired, but enough information that piques your curiosity. So join me and let me show you my passion. Hey all, welcome back to another edition of Quarantine Science. Now, you may notice I'm grinning from ear to ear because today we're going to have some fun. By fun, in my world, if you haven't figured it out, fun equals destruction. It's undeniable math, okay? Just saying. Now, we're going to break something today. And this experiment you've probably seen before. It's the wine glass experiment. Now what I've done though, I'm adding a little bit of my own twist to it because I really was interested in this, which is the vibrational aspect. Because to do this, you have to use its natural frequency. The frequency that everything naturally vibrates at. Now each item or each material and geometry has its own natural frequency. And we'll get into how you find that in just a moment. But I want to go ahead and start you off with how my setup is, what my rig looks like, and how I plan to do all this measuring. All right. So here we are. Here's my setup. We have my computer with my oscilloscope software on it. All right. And now it does have hardware that's attached. The hardware here sends a signal out, which I use the software to dictate what frequency I want that signal. That's going to my receiver. That then runs over to my subwoofer, which I've bypassed the amplifier and the subwoofer connected straight to the speaker. So we can bypass those high frequency filters. On top of that, my oscilloscope hardware, we can measure through one of the channels. This little doohickey here, which is an accelerometer, has a power supply and a step down from 9 volts to 3.5 volts. And what that's going to do is, since the glass is mounted to the plate, the glass will vibrate and it will vibrate the metal plate. All right? That vibration is then picked up by the accelerometer. And then it goes back to my computer, and you will be able to see it along this line. And I'll have I'll have a screenshot set up to where you can see the vibrations as they occur. Now, how does this experiment work? Well, we find the natural frequency of the glass. All right. How do you do that? Well, the old trick is take your finger, dip it in some water, run it around the rim. When you do this, what you're doing is you're creating friction, which creates a vibration, and then the glass starts to vibrate at its natural frequency. It's pretty cool, right? And when you've probably done that at dinner parties or whatnot, goofing around, but that's the natural frequency. What we intend to do is we intend to use the oscilloscope to pump the natural frequency. We're going to amplify it. We're going to create an amplitude greater than that glass can handle. All right? And that glass will start to vibrate and wobble and hopefully break. So we're going to check all this out, and you're going to hear probably voiceover, because if I were to run this noise, this would get annoying. All right? So check it out. Here is the experiment. Now we have the split screen going. On the left-hand side, you notice we have the wine glass. And on the right-hand side, we have the oscilloscope. The upper portion of the oscilloscope is the response portion. This is the vibrations that are coming off the wine glass through the metal plate to the accelerometer. And the lower portion is our input frequency. That's what we're going to send to the amplifier over to the speaker. In a moment, we will turn up towards the natural frequency, and you'll notice that the excitation, the upper portion of the oscilloscope, will grow. Currently, though, we have it set at 417 hertz, and you can see me kind of messing around, making sure all my cameras are set. And there's really no vibration. Now, what I do want you to pay attention to is kind of those reflections in the glass, and the upper rim will really start to distort as we get into the natural frequency. Now I just moved it up to 427 hertz, really no response. Here we go, 437.6 hertz. Now you notice that the oscilloscope, the response portion, has grown a little bit. And as we turn up the amplitude, which is the volume, notice that it starts to grow. In a moment, you're going to start seeing the glass shake. I'm really kind of turning it up slowly, but the vibrations in the bell of the glass are carrying right down the stem, right over to the accelerometer. And you'll start seeing some of the warping. And around the rim, it will start to fuzz like it's blurring. It's really not blurring, it's just vibrating. And we continue to increase the decibels output, and bam, there you go. Look at that. That was beautiful. Now I'll back it up here in a moment, and I'm going to give you a screenshot of the glass breaking, because this is just absolute fun. So now it's slow-mo time. Let's take a look at this, because this gets really interesting. If you watch the center of the glass right at the top where the stem meets, you can actually see where this crack begins to initiate and propagate up the bell. Now take a look. I'm going to back this up for a second so you can see this. Check this out. It begins in the center, and then bam, it's growing, and then just splits. Now I wanted to pause for just a moment and get a little super nerd on you and talk about the mechanics of the failure of the glass at a molecular level. Now when we look at it at this level, we notice that the atoms of the glass are formed in a lattice structure. And what that means is that it's highly organized in a pattern that repeats itself over and over again throughout the material. Now this lattice is formed in the manufacturing process as the glass transitions from a molten state to a hardened state. But not all the time does this lattice structure form perfectly. Sometimes atom chains will be misaligned. And when we vibrate the glass, a high mechanical state, it allows chains to break and reconnect or realign with misaligned chains above it or near it, beside it. And if you get enough of these, they will form micro cracks. And these micro cracks will just continue to propagate through the glass as they move away from high energy, mechanical energy areas such as the bell of the glass or the rim of the glass, down to the base of the glass around the stem where it's not moving as much. And eventually what we see is catastrophic failure. Well, that's all I have for you for today. Thank you for watching the video. If you've made it this far, huge thank you. Also, if you liked the video, hit the thumbs up button. If you really liked it, smash it, but I won't be able to tell whether you smashed it or just hit it. So, throw a comment in the comments below. If you have any questions regarding the science behind the experiment or even my setup or my gear, also put those in the comments and I'll be happy to answer those questions. I have more videos coming up in the future. I've got one in the works, and hopefully Melanie won't kick me out of the house for all my shenanigans. Big, huge thanks to her for letting me make a mess of the living room, all in the name of science. Remember, if you're destroying something, it's fun, but it's funner if you use science to destroy it. So look forward to my future videos, and I will catch you in the next one.